Good morning. Yes, in the last classes we discussed about the DIT-FFT algorithm. DIT-FFT algorithm. What is meant by DIT-FFT algorithm? What is meant by DIT-FFT? Decimation in time, fast Fourier transform. Okay, decimation in time, fast Fourier transform. Decimation. This is also called as radix 2. Radix 2. Radix 2. Decimation in time, fast Fourier transform. Right. Okay. So and we have done some problems also on DIT FFT algorithm. We have two classes of FFT as we already know. So those are DIT FFT, that is decimation in time fast Fourier transform, and decimation in frequency fast Fourier transform. What it deal decimation in time FFT deals with decomposition. Decomposition of the sequence starts from lowest level to highest level. Suppose if we take 8-point DFT. So how to decompose it? It starts from 2-point DFT, then 4-point DFT, and then finally 8-point DFT. So 2-point DFT, 4-point DFT, and 8-point DFT. Like that, it will be decomposed and combined. Whereas coming to the DIF FFT algorithm, here the output sequence X of k is divided into smaller and smaller sequences. It means that it starts from higher components to lower components. Suppose 8-point DFT is there, so it will take first 8-point DFT as the input. After that, it will be decomposed into 4-point DFT, two 4-point DFTs, and then these 2 4-point DFTs will be decomposed as two 2-points. So finally, 4 2-points DFTs will come as the output. So it is decomposed like this. So this is the algorithm, DIF algorithm. The output sequence X of k is divided into smaller and smaller subsequences. So 8 points to 4 points, 4 points to 2 points. In the for 16-point and 32-point DFT also, DIF FFT also it's like that. Suppose if you take 16-point, first of all 16-point, it will be divided into 2 8-points. And these 8 points, 2 8-points are divided into 4 4-points, and these 4 4-points are divided into 8 2-points FFTs, right? Like that, it will be decomposed, right? So the input sequence X of n is partitioned into two sequences, each of length n by 2 samples, right? So the first sequence X1 of n consists of first n by 2 samples of X of n, and second sequence X2 of n consists of last n by 2 samples of X by n. So here X1 of n is X of n, that is even numbers, that is n equal to 0, 1, 2, 3 up to n by 2 minus 1, and X2 of n equal to X of n plus capital N by 2. Okay, X of n plus capital N by 2, where n is equal to 0, 1, 2, 3 up to n by 2 minus 1, right? 1 by 2 minus 1. Okay, next, if n equal to 8, the first sequence X1 of n has values for 0 is less than or equal to n is less than or equal to 3, and X2 of n has values for 4 to 7. 4 is less than or equal to n is less than or equal to 7, right? So the n-point DFT of X of n can be written as we already know that this is a n-point DFT. So X of k is equal to sigma n equal to 0 to n by 2 minus 1 X of n into Wn power nk plus sigma n equal to 0 to n by 2 minus 1 X of n into Wn power nk, right? Okay, so first one is even indexed one, and second one is odd indexed one. Okay, so even indexed one, this is even indexed one. So sigma n equal 0 to n by 2 minus 1 into X of x1, let it be taken as x1 of n. X1 of n into Wn power nk plus sigma n equal 0 to n by 2 minus 1 x2 of n into Wn power n plus n by 2 into k. So here x2 of n is x of n plus n by 2. Okay, that is odd indexed one. Okay, so it is sigma n equal 0 to n by 2 minus 1 x1 of n into Wn power nk plus sigma n equal 0 to n by 2 minus 1 into x2 of n into Wn power nk into Wn power n by 2 into k, right? Okay, okay. So we can write this as sigma n equal 0 to n by 2 minus 1 into x1 of n into Wn power nk plus extract this Wn power n by 2 into k. So Wn power nk by 2 into sigma n equal 0 to n minus 1 2 n by 2 minus 1 into x2 of n into wn power nk, right? So it will become sigma n equal 0 to n by 2 minus 1 into x1 of n into wn power nk plus e power minus j by k e power wn power nk by 2 will become here wn equal to e power minus j 2 pi n, right? So e power minus j 2 pi by n whole power nk by 2, right? 2 pi by n into whole power nk by 2. So n and n gets cancelled, 2 and 2 gets cancelled. So it will become e power minus j pi k. So replace this wn power nk by 2 by e power minus j pi k into sigma n equal 0 to n by 2 minus 1 into x2 of n into wn power n. When k is even, so e power minus j into pi k is equal to e power minus j pi is equal to 1, right? So when k is even, so x of 2k is equal to sigma n is 0 to n by 2 minus 1 x1 of n in wn power 2k 2nk. Okay, even, it is even. Then plus this is 1, its value is 1. Okay, then sigma n equal to 0 to n by 2 minus 1 x2 of n into wn power 2nk, right? So sigma n equal to 0 to n by 2 minus 1 is taken as common, x1 of n minus x2 of n into wn power 2nk, or we can write this as wn square as wn by 2. Okay, w suffix n by 2, wn power 2 can be written as w or it is w suffix n by 2 to the power n k, right? So this is equation number 11. Equation number 11. So that is sigma n equal 0 to n by 2 minus 1 into x1 of n plus x2 of n into whole into w suffix n by 2 power n by nk. So let it be taken as f of n. So equation 1 is n by 2 point, this is equation number 1, n by 2 point DFT of the n by 2 point sequence obtained by adding the first half and last half of the input sequence. Okay, if k is even. Similarly, when k is odd, if e power minus j by k is equal to minus 1, if it k is odd, then it will become e power j by k is equal to minus 1. Okay, so replace k by 2k plus 1. Okay, 2k plus 1. So sigma 2k 2k plus 1. Okay, in the DAT destination in time FFT, we will replace 2n plus 1, right? But here this is DIF FFT, so we will replace even indexed by 2k and odd indexed by 2k plus 1, right? So sigma n equal to 0 to n by 2 minus 1 whole into x1 of n minus x2 of n into wn power 2k plus 1 into n, right? Or we can extract this as wn power 2kn into wn power n. Okay, okay. So it will become sigma n equal to 0 to n by 2 minus 1 x1 of n minus x2 of n whole into wn power n into wn power 2nk. Or we can write this as w suffix n by 2 power n by nk, right? So this will be considered as a g of n, whereas x1 of n plus x2 of n will be considered as f of n, and x1 of n into x2 of n whole power wn power n will be considered as g of n into wn by 2 power n by k. Let it be considered as equation number 2. So equation number 2 is n by 2 point DFT of the sequence obtained by subtracting the second half of the input sequence from the first half and multiplying the resulting sequence by wn power n. Okay, wn power n. So equation 1 and 2. Here equations 1 and 2. What is equation number 1? That is sigma n equal 0 to n by 2. That is x of 2k equal to sigma n equal 0 to n by 2 minus 1 into x1 of n plus x2 of n into w suffix n by 2 power nk. And equation 2, that is x of 2k plus 1 is equal to sigma n equal 0 to n by 2 minus 1 into x1 of n minus x2 of n whole into wn power n into wn suffix n by 2 whole power nk. These two equations shows that the even and odd samples of the DFT can be obtained from the n by 2 point DFTs of f of n and g of n respectively, where f of n is x1 of n plus x2 of n, where n equal to 0 to 0, 1 to up to n by 2 minus 1, and g of n is x1 of n excuse me, minus x2 of n whole into wn power n, where n is varying from 0 to n by 2 minus 1. Let it be considered as equation number 3. So equation number 3 can be represented by butterfly diagram. Butterfly diagram. In DIFFT also will represent the butterfly diagram. So here the butterfly diagram can be represented like this. So as shown as the flow graph of basic butterfly diagram for DIF algorithm is this is x1 of n, this is x2 of n, this is weighing function wn of n will be at here. It will be at here. Whereas in DIT, it will be at here, wn power n. Okay. So first of all, we will get f of n, that is x1 of n plus x2 of n. And we will get g of n at here. What is g of n? X1 of n minus x2 of n whole into wn power n. Okay, x1 of n minus x2 of n whole into wn power n, whereas f of n is x1 of n plus x2 of n only. Okay, so from equation number 1, x of 2k is sigma n equal to 0 to n by 2 if n is 8. Okay, if you take n is 8, so equation number 1 will become sigma n equal to 0 to n by 2 minus 1 into x1 of n plus x2 of n and wn power 2nk. Okay. Okay, so it will become if k is 0, here k is varying from 0 to n by 2 minus 1. N by 2 is 8 by 2, that is 4 minus 1, that is 3. Okay, so 0 to 3, right? 0 to 3, 0 to 3. So by substituting the values of k equal to 0, k equal to 0, it will become f of 0. N is varying from 4 minus 1, that is 3. N is varying from 3, 0 to 3. K, if k is 0, so we'll get the value of x of 0 is like this: f of 0 into w8 power 0 plus f of 1 into w8 power 0 plus f of 2 into w8 power 0 plus f of 3 into w8 power 0. W8 power 0 is 1. W8 power 1 is, by using the formula, we can calculate these values. Okay, so what is the formula? The formula is already discussed in our earlier cases. So see, e power minus j 2 pi by n is wn. wn wn power 0, that is w8 power 0. W8 power 0 is e power minus j 2 pi by n whole power 0, like that. We will substitute. In this one. Okay, wn is e power minus j pi by n whole power 2. Okay, like that. So by substituting these values, we will get W8 for 1 value is this one, W8 for 2 value is minus J, W8 for 3 is minus 0.707 minus J 0.707, W8 for 4 is minus 1, W8 for 5 is minus 0.707 plus J 0.707, W8 for 6 is J, W8 for 7, like this we will calculate. Okay, we will calculate those values, right? Then if k equal to 0, we will get by substituting these values in this expression, we will get f of 0 plus f of 1 plus f of 2 plus f of 3. If k equal to 0, x of 0 is this one. If k equal to 1, x of 2 is sigma n equal to 0 to 4, 0 to 3, 4 minus 1 is 3. So f of n into wn power 2nk. So that by substituting these values, we will get f of 0 plus f of 1 into minus j plus f of 2 into minus 1 plus f of 3. If k equal to 2 and simply substitute those values, we will get f of 0 minus f of 1 plus f of 2 minus f of 3. If k is 3, we will get f of 0 plus f of 1 plus f of 1, f of 2 plus f of 3 whole into minus w8 power 2 whole power n. Okay, so by simply substituting those values, we will get f of 0 minus f of 1 and w8 power 3 minus f of 2 plus f of 3 into w8 power 2. From equation number 2, equation number 2 is sigma, that is x of 2n plus 1, x of 2k plus 1. So this is equation number 2. That is sigma n equal to 0 to n by 2 minus 1, x1 of n minus x2 of n into wn power n into w n by 2 power nk. Okay, so by simply substituting k values from 4 to 7, okay, K value is K equal 0 to 3. In this expression, we will get the values of x of g, x of 1, x of 3, x of 5, and x of 7 odd indexed values. So like this. Okay, these are these values. So even valid samples of x of t can be obtained from the 4-point DFT of the sequence f of n, where f of n is x1 of n plus x2 of n, where n is varying from 0 to n by 2 minus 1. Those are f of 0 equal to x1 of 0 plus x2 of 0. F of 1 is x1 of 1 plus x2 of 1. F of 2 is x1 of x2 of 1 plus x2 of 1. X1 of 2 plus x2 of 2, and f of 3 is x1 of 3 plus x2 of 3, right? Similarly, odd valid samples of x of k can be obtained from the 4-point DFT of sequence g of n, where g of n equal to x1 of n minus x2 of n into w power n. Those are g of 0. So x1 of 0 minus x2 of 0 whole into w power 0. G of 1 is x1 of 1 minus x2 of 1 into w power 1, and g of 2 is x2 of x1 of 2 minus x2 of 2 whole into w power 2, and g of 3 is x1 of 3 minus x2 of 3 whole into w power 3. Using the above information and the butterfly structure for 8-point DFT is like this. So these are the values: x1 of 0, x1 of 1, x1 of 2, x1 of 3. Similarly, x1 of 2, this is x2 of 0, x2 of 1, x2 of 2, and x2 of 3. These are odd indexed values, even indexed values, and these are odd indexed values, right? Okay, this is x of 0, x of 1, x of 2, x of 3. This is x of 4, x of 5, x of 6, and x of 7. So this is a 8-point. It will be goes to the stage 2, that is a 2 4-point DFTs. 4-point means n by 2 point. Here it is n equal to 8. So this is a 4-point DFT and 4-point DFT. This is f of 0, f of 1, f of 2, f of 3. And this is g of 0, g of 1, g of 2, g of 3. Finally, we will get x of 0, x of 2, x of 4, x of 6. These are the even samples of x of k, whereas these are x of 1, x of 3, x of 5, x of 7. These are odd samples of x of k. So this is the reduction of an 8-point DFT to 2 4-point DFTs by decimation in frequency. That is a decimation in frequency, DIF FFT, DIF FFT, right? Now each n by 2 point DFT can be computed by combining the first half and the last half of the input points for each of the n by 2 point DFTs, and then computing n by 4 point DFTs. Okay, so these are n by 2 point DFTs, then n by 4 point DFTs. Okay, so flow graph of decimation and frequency decomposition of 8-point DFT into 4 2-point DFT competitions is like this. So this is 8-point DFT. After that, 2 4-point DFTs, and these will be decomposed as 4 2-point DFTs like this. Okay, so these are 8. This is 8-point DFT. Okay, then 4-point DFTs. Okay, so here the this is fiddle factor will be W840, W841, W842, W843. Here W840, W842. Okay, this is also W840, W842. Okay, finally we'll get this is the final result. Okay, x of 0, x of 4, x of 2, x of 6, x of 1, x of 5, and x of 3, x of 7. Like this, it will be decomposed into 4 points and then 8 points. 2 points, and 4 points. Fiddle factor. Okay, this is the fiddle factor. Okay, now we'll see the flow graph of 8-point DIFFT algorithm will be like this. By simply substituting those values, we will get the final output as this one. Okay, this is the basic computational. So this is the flow graph of 8-point DIFFT algorithm. DIFFT algorithm. Next, coming to the basic computational diagram for DIFFT. Basic computation. This is the basic butterfly model. Okay, so A and B are the inputs. This is the fiddle factor Wn for n. Okay, so here we will get A plus B, and this is A minus B into this fiddle factor, A minus B into Wn power n. Okay, so summary of steps of radix to DIFFT algorithm will be like this. First point is the number of input samples, that is n equal to 2 power m, where m is number of stages. M is number of stages. How many stages are there here also? If n is 8, we have 3 stages, 2 power 3 stages. Okay, so 2 power 3, so that m is 3, so that we have 3 stages. If n is 16, then we have 4 stages. Okay, m is 4, then we have 4 stages. Second point is the input sequence is in natural order. And the third point is the number of stages in the flow graph is given by m equal to log n to the base 2, log n to the base 2. Okay, log n to the base 2. Right. And then coming to the fourth point, each stage consisting of n by 2 butterflies. Each stage consisting of, and it will be divided into 2 stages. Each stage will be divided into 2 stages. Suppose if it is 16, then it will be divided into 8 point DIFFT and 8 point D. 8 is divided into 2 stages. Again, 8 by 2, that is 4, 4. 4 is divided into again 2 stages. 4 by 2, that is 2, 2. Okay, right? So that is n by 2 butterflies. Okay. Input minus outputs for each butterfly are separated by 2 power m minus m samples. M, or it is also called as a m stage index. That is, for first stage m equal to 1, and for second stage m equal to, and so on. And next point is the number of complex multiplication is given by n by 2 log n to the base 2. The number of complex addition is given by n log n to the base 2. The tittle factor exponents are a function of the stage index m, and is given by k equal to nt by 2 power m minus m plus 1, where t is varying from 0 to 2 power m minus m minus 1. Okay, so next point is the number of sets or sections of butterflies in each stage is given by the formula 2 power m minus 1. Okay, then last point is the exponent repeat factor ERF, that is called ERF, which is the number of times the exponent sequence associated with the n repeated is given by 2 power m minus 1. These are the summary of steps of radix to DIFFT algorithm. Okay, next coming to the differences and similarities between DIT and DIF algorithms. This DIT means decimation in time FFT, and decimation in frequency FFT, right? Okay, similarities. What are the similarities, and as well as differences also? Similarities and differences. Okay, similarities and differences. Okay, right. So first of all, we'll see the differences. So for DIT, the input is a bit reversed while the output is in natural order, right? So input is bit reversed. How to get bit reversed already we saw in the previous problems. Okay. So input is bit reversed and output is in order, natural order. So in DIF, the input is in natural order while the output is in bit reversal. Okay. So next difference is in DIF, butterfly is slightly different from the DIT, where in DIF the complex multiplication takes place after the add subtract operation. So in DIF the complex multiplication takes place. So it is represented by G of n, it is x1 of n minus x2 of n into Wn power 10k, right? So this is the complex multiplication take place after the add subtract operation. These two are the differences of DIT and DIF FFTs. And coming to the similarities, so both algorithms requires n log n to the base 2 operations to compute the DFT. Both algorithms can be done in place, and both need to perform bit reversal at some place during the computation. Okay, these are the similarities of DIT and DIF FFTs. Okay, next coming to the problems, we'll do some problems also. Okay, these are all the problems we have to do it. Okay, taking a paper and do it. Then only we can easily understand the problem. Okay, see the problem. See, okay, coming to the problem. See, compute 8-point DFT of the sequence. So here x of n equal to 1 for 0 is less than or equal to n is less than or equal to 7 and is 0 otherwise by using DIT and DIF algorithms. So the hidden factors associated with the butterflies can be found as W for 0 equal to 1 and W for 1 is so how to get these hidden factors already we discussed, right? So by simply substituting those values, we will get the hidden factor values are like this. W for 0 is 1, W for 1 is 0.707 minus J 0.707, and W for 2 is minus J, and W for 3 is minus 0.707 minus J 0.707, right? First of all, we will solve the DIT-FFT algorithm, okay? So the here if you take DIT effect algorithm, here the first input values are bit reversal values, and output values will get natural order. Okay, so all these bit reversal values, all these values x of n values are one only. It is given as 1 from 0 to 7. Okay, so anyhow all these values are 1 only. Okay, so it will be decomposed from smallest level to highest level. So this is a 2-point DFT, 4-point DFT, and then 8-point DFT. Okay, so this is W840, W840, W840 fiddle factor. Here W840, W842. Okay, like this. This is W840, W841, W842, W843. Finally, we will get all these values are 8. X of 0 is 8. Remaining all values are zeros. This is the 80FFT for the given problem. And for the same problem, DIFFT, DIFFT also. So here these values are in natural order and these values are in bit reversal order. Okay, so it will be decomposed from smallest level to highest level. So first of all, this is 8-point DFT. After that, it will be decomposed into two 4-point DFTs. So and then it will be decomposed into four 2-points DFTs, four 2-point DFTs, right? So by simply substituting those values, so we will get the final result is x of a equal to 8, 0, 0, 0, all remaining zeros. Okay, like this we can solve the problems. So similarly, this is the another problem. Find the DFT of a sequence x of n is equal to 1, 2, 3, 4, 4, 3, 2, 1 using DIF algorithm. Fiddle factor associated with the program are given. Okay, so this is the basic butterfly model, right? This will get a plus b, and this will get a minus b into w n power k. Okay, okay, right. So by DIF FFT algorithm, we can solve the problem like this. Okay, so 10 minutes time is there. Next coming to the how to calculate these values like this. Okay, so next compute 8-point DFT of the sequence x of n equal to 1 for 0 is less than or equal to n is less than or equal to 7 and it is 0 otherwise, then it is already solved this problem. 8-point DFT. Again 4-point DFT of sequence of 0, 1, 2, 3. It is simple one. Okay, we can do it. Next, coming to the IDFT using FFT algorithm. Discrete inverse discrete Fourier transform. Okay, inverse discrete Fourier transform. So FFT algorithms can be used to compute an inverse DFT without any change in the algorithm. FFT algorithms can be used to compute an inverse DFT without any change in the algorithm. The inverse DFT of n-point sequence x of k where k is varying from 0 to n minus 1 is defined as x of n equal 1 by n sigma k equal 0 to n minus 1 x of k into e power plus j 2 pi n k by n. Okay, it is equal to 1 by n into sigma k equal 0 to n minus 1 x of k into w n power e power minus j 2 pi n 2 pi by n is considered as w n. So w n power minus n k, right? Right? Fiddle factor. This is fiddle factor. So take complex conjugate and multiply by n. We obtain multiply by n and taking complex conjugate. So n into x star of n is equal 1 by n into sigma k equal 0 to n minus 1 x star of k into w n power n k, right? Why? Because it is a complex conjugate, right? So sigma n equal to 0, k equal to 0, sigma k equal to 0 to n minus 1 x star of k into w n power n k, or it is sigma k equal to 0 to n minus 1 x star of k into w n power n k. That is considered as equation number 1. So the right hand side of equation number 1 is DFT of the sequence x star of k and may be computed using any FFT algorithm. The desired output sequence x of n can then found by complex conjugating the DFT and dividing by n to give n by n, the x of n equal to 1 by n into sigma k equal to 0 to n minus 1 x star of k into wn power n k whole star. So compute IFT of the sequence. This is the IFT of the sequence. So x of k equal to 7. This is x of 0, x of 1, x of 2, x of 3, x of 4, x of 5, and x of 6 and x of 7 values are given like this. We have to compute this IDFT of the sequence using DIT algorithm, decimation in time algorithm. Okay, decimation in time algorithm. So taking complex conjugate of x of k and apply bit reversal index inputs to flow graph of n point DIT algorithm. So these will be like this. So this is complex conjugate of x of k and bit reversal. Here the inputs will be bit reversal and will get the natural order at the output side if it is DIT FFT, right? So remaining everything is same procedure. Okay. So bit reversal, these are the bit reversal values and same procedure. Okay, so that we'll get n into x star of n or x of n equal to multiply by n into this one. So n by n into n, so that we'll get x of n is 1 1 all ones and last one is 0. Okay. Next, find the IDFT of the sequence. This is the sequence given using DIF algorithm. So here the order will be normal order and here will be bit reversal order. Okay, so normal order these values are given. So using the same procedure we will solve this problem so that we will get bit reversal values like this. Okay, so x star of n will be like this and divide it by 1 by n. So 1 by n into this these values, so that it will be n into 1 by n. 8 and 8 gets cancelled, so that it will become all 4 ones and remaining are zeros. Okay, so this is the calculation how to get these values. Okay, so evaluate and compare. Next, evaluate and compare 8 point for the following sequence using the DIT algorithm. A is given x1 of n equal 1 for minus 3 is less than or equal to n is less than or equal to 3 and x1 it is given as 0 otherwise. Similarly, b bit is given as x2 of n is 1 for 0 is less than or equal to n is less than or equal to 6 and it is 0 otherwise. So we have to evaluate 8 point for the following sequence using DIT FFT algorithm. Okay, so you can solve this problem. This is a normal problem, not IDFT. This is DFT only. Okay, so we can solve this problem, right? So by solving this, we will get the answers as x1 of n is like this one and x2 of n is this one. Okay, you can solve this problem. Okay, so this second unit, that is discrete Fourier transform, discrete Fourier series. Okay, and fast Fourier transform. In this fast Fourier transform, we have two classes. Those are decimation in time fast Fourier transform and decimation in frequency fast Fourier transform algorithms, uh, general procedure, and we solved some problems also. Butterfly models. These problems are very important. Butterfly model problems are very important. Okay, so in both cases, DIT as well as DIFFT, right? So concentrate concentrate on these two classes, DIT and DIFFT classes. Okay, right? So definitely they may ask essay questions based on this DIT algorithm and DIFFT algorithm. These are the sure questions from this unit. Okay, compulsory questions. So concentrate concentrate on it. Okay. With this, I'm concluding the today's class. Tomorrow, day after tomorrow, we'll start the next unit. Okay. Okay. Thank you, one and all.